Language Department. Now I'm going to start this session and I'm the host of the session. Firstly, I'm going to introduce our honorable speaker of this session, Dr. Pradipto Kumar Banerjee. He is a professor and head of CSE AIML at the Future Institute of Technology, Kolkata, with over 20 years of teaching and research experience. He holds a PhD in technology from the University of Calcutta in the field of pattern recognition with a focus on face recognition. His research interests span machine learning, deep learning, face recognition, and multimodal emotion analysis. He has published widely in reputed journals and conferences of Springer, Elsevier, IEEE, and Taylor and Francis, in addition to authoring a book with CRC Press and contributing several book chapters. Dr. Banerjee has received multiple academic medals and awards for excellence during his undergraduate studies in physics. He has mentored nationally recognized projects under DRDO and INAE initiatives and successfully led funded research with WBPCB and TERI. He is also a reviewer for leading international journals and an active member of ACM, CSI, IACSIT, and IAENG. Now I'd like to request Dr. Banerjee to take over the session. Thank you.
Okay, thank you, madam. Very good afternoon. Can you hear me? Am I audible to everyone? Am I audible, madam?
Yes, sir.
Yes, sir. You are audible.
Okay. Okay, with your kind permission, can I start the presentation? And
Yes, yes, yes.
yeah, and I'm turning off my video. Okay, if with your permission. Okay.
Okay, sir.
Okay. 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 This one is visible now. This slide is visible. My presentation.
Yes, sir. Yes, sir. It's absolutely visible.
Okay. Thank you. So good afternoon to everyone. So my topic for today's lecture is effective computing applications in next generation Indian made tech. So here we have uh, written that from emotions to actions. Hope this annotation is visible also to everyone. So what is from emotions to actions and what is effective computing? The story goes over here. That is, we are taking the actions. We are taking the actions through effective computing, and we are taking the gathering the data from the emotions. That is the mood story uh, of this lecture, and that is we are getting the data from emotion. That is, we are getting the data from the emotion and taking action through the effective computing. So this is the nation. This is the notion of this talk. Okay. So what is the outline? What is effective computing? We will discuss in very little brief what is effective computing and what is the how it is relevant in the recent days. Why we need the effective computing now, and what is the foundations of emotions. That is, we need to know what is before going to emotion recognition. We need to know what is affect and what is emotion. These two are very important. What is affect and what is emotion? These are very much interrelated. So we will deal a bit with affect and emotion. And as because we are going to model our emotions, as because we are going to model our emotions, so some theory of emotion, how emotion is coming, and what is the background of the emotion, how emotion is constructed. So we need to know all these things. In brief, we discuss the theory of emotion because emotion modeling needs the theory of emotion, the background of the emotion, how actually the emotion is being constructed. Okay. Then we have the signals and the pipelines. We'll discuss about this one. Here we will see what type of signals and patterns and how they are extracted and how we can use these signals or features for learning uh, the systems and all these things. And this is we can say this is the affect sensing part, and there is the different types of modalities are there. So there are different types of modalities. We have the face modalities, we may have the voice modalities like this, and we have text modalities, and we have the physiological signal. Okay, so physiological signal, this type of modalities we have. So in our lecture or in our talk, we discuss only the face modalities. Only one modality we will discuss over here. And what I believe that if we the idea of emotion recognition through face expression analysis or through facial emotion recognition, the idea we develop that can be extended also to other modalities, that is like speech or text or physiological signals. Okay, and then we will see how we can process the emotion and how we can estimate the effects and how we can predict the emotions. Okay, emotion, there is a relation between emotion and physiology. Also, and last but not the least, that is the what is emotional robot and what is a medtech application. So, uh, before going to the details of the lecture or the study, I would like to mention that this talk is very much introductory and the beginners level of for affective computing. Those who are interested in affective computing in deep and want to further research or further state of the art material, if they need, they can see or go through the IEEE transactions on affective computing or multimedia. There are several state of art papers in IEEE International Conference of CVF, that is Computer Vision and IEEE CVP. They're very rich resources there, and one must have a very popular and book that very popular and good book, that is Affective Computing, which is written by Rosalind W. Pickett. That is from 1997, from published in from MIT Press. So again, I mentioned that this is a very introductory and beginners level of affective computing studies. Okay, so we start with what is affective computing, right? So what is our aim? Our aim is to building the computers, right? Our aim is building the computers that can sense, that can understand, or that can respond to human affect. So what is affect? Affect is nothing but how we feel, simply a raw feeling. Simply, affect is nothing but the raw feeling, a raw feeling too, simply. And how energized they are. That means there is an intensity. So that is affect. Only these things. Raw feeling, no emotion is there. Raw feeling tone and the intensity. With the intensity, how much we have the positive valence, how much we have the positive feeling, how much we have the negative feeling, how much whether I have or we have the positive feeling or negative feeling, and what is the intensity of that feeling. So that is affect. So we need to build our computer so that it can sense or understand that what is the human affect, and also try to respond accordingly. And then comes the emotion. Then comes the emotion, that is how we are expressing, how strongly we show that. So that means we are trying to build a computer which can feel actually the human. That is the objective, main objective of affective computing. The one more thing, that is affect is very raw feeling tone, but emotion is constructive. We will see later that why it is constructive. It is very complex and constructive nature. So constructive feeling is emotion and raw feeling is affect. Okay, so constructive feeling is emotion, and raw feeling corresponds to affect. So this is the affective computing. We want to sense, understand, and place. So now, why do we need the affective computing now? So there are doctors, nurse, and psychologists are there. They are doing their job. Okay, no affective computing. Without affective computing, they are doing their job very well, years after years. Say, for an example, a depressed patient goes to the clinic, visit the doctors, and talk for 20 minutes. Okay, doctor prescribes, and they come back home. That is the process of the treatment. Okay, so years after years it is going on, and okay, the system is okay. So there are no need of effective computing, or no AI is needed actually over here. But why we need effective computing? Why it is very useful for recent days? That is, the problem here, the thing is episodic. That means the how the care happens. That means patient visit once in a month. Okay, between once in a month or once in 3 months. That is the problem. Between this visit, we know nothing. Again, the treatment is subjective. When we are dealing with the emotions, when we are dealing with the expressions of a person, when we are dealing with the anxiety, stress, or depression, then if it is a subjective, then it is tough to understand. Because if a doctor says that, how are you feeling? The patient says, okay, I'm fine. How could you know that he's telling the truth or he's honest? So there is another problem, that is a subjective problem. Another, last but not the least, that is the delayed problem. Why we react after the crisis, and already things get worsened. Okay, so our motto is not the motto of the effective computing is not that conflicting with the no conflict with the human judgment, or no conflicting with the clinical treatment, but it assists. How? Because effective computing can add something with this. What it is adding? That is the continuous monitoring, which adds the continuous monitoring. Number one. And number two, the objective treatment. That is the measurable signals, numbers, signals or numbers like this. But that is not just feeling, that is not subjective, but it is the objective data we have. And also the scalable signals, not like one doctor and one patient thing. It is can be done for many people, many people. It is a scalable thing. So effective computing, why it is needed? Because it is bridging the gap between the traditional treatment and real world emotion dynamics. Okay, so and let's have an example with the depression monitoring beyond the clinic. So say we have the with the objective data, what effective computing can do, that is, it can continuously monitoring. Say John, he visits the psychiatrist once in a month. During a 20-minute session, he says he's doing okay, but that is not enough. Why we need effective computing? It continuously monitoring through, say, John has a mobile app, say has a mobile app, which can continuously monitors, or a smartwatch, not only a also a smartwatch is there. So uh, effective computing can continuously monitor the conversation with the app. It can track the sleep patterns, or if there is any facial expression changes, like fewer smiles or poor sleeps, like this. So it is a continuous monitoring. And for this whole month, 24 into 7 and whole month, not a single snapshot of 20-minute uh, life at a clinic. 20-minute snapshot is not there. It is a continuous monitoring system. So what is the benefit of this? Benefit is we can the early treatment can be started. Okay, so before we have discussed also that what is the difference between the subjective treatment and objective treatment. So here also the main difference of the subjective treatment and objective treatment is that uh, subjective treatment basically it depends on the perspective. That is feelings, opinions, personal experience, a patient's own word, own feeling. But objective treatment depends, as we know, that it depends on the facts, measurements, and independent of the personal feeling or mood. So objective data is independent, and affective computing dealing with the trying to dealing with the why I'm saying trying, I will discuss later. So it tries to deal with the objective data, which is independent of the personal feeling. Okay, so that our aim is to transform the subjective feelings to the objective measurable data. I repeat that our aim of the affective computing to transform the subjective emotions into objective measurable signals or objective data. Okay. So another problems with the subjective treatment, I'm not going in details of this because there are basically two types of problems with the subjective treatment. One is bias. That is both the doctor and the participant may be biased. Okay, so it depends on the personal feelings. What type of question doctor is asking and what type of answer the patient is giving according to this. So it influences the assessment and the outcome. So it is a bias, and there is a systematic bias which involves that in which order the question is the sequence. What is the sequence of the questions or halo effects, something like this. So and also one more important problem is that is lack of objectivity and reliability. That is uncorrelated with the objective data. That means the patient is saying that okay, I am taking my pills regularly, but pill counts or biomarker show that no, there is a low adherence. So that means there is a problem with the subjective treatment and inconsistency is there. So what is the aim? This is the aim of affective computing. That is, okay, subjective, the patient reported to the clinic that is, I feel completely hopeless. Okay, fine. Nothing gives me pleasure anymore. And this is reported by the patient. And the clinician is observed that therapist notes that the bake depression inventory, that is course is very poor and there is a severe depression is there. Fine. Now, where is affective computing? What it does? It it measures the low expressivity and few smiles. That means it regularly check the facial expression recognition. It check there is a monotone tone. That means the longer pauses in speech. Also low HRV. HRV is low. Fewer smiles and longer pauses in speech. So it is the continuous monitoring. I mean to say this is the continuous monitoring. Continuous monitoring. So what is our aim? Just like we track BP, blood pressure, or temperature with continuous data, one day we can track or monitor stress level, anxiety level, emotional well-being level. So that is the objective of affective computing. Today scenario, we have both uh, we can measure the BP continuously, we can measure the temperature continuously. One day we can measure the stress level continuously, anxiety level continuously, and also the emotional level. So we show one example of how affective computing helps us. So look at the picture. So this picture, there are two pictures, two images are there. This shows the two different child while watching the same videos. This is child one, this is child one, and this is child two watching the video. Child one is watching the video, child two is watching the video, and video of a child who is playing. This is the same person. In the video, in the picture, the person is same. That is the child is same. But child one is has a typical brain development. That means that is normal. Okay. But child two having autism, brain development is not typical brain development is there. So left is normal and the right is the with the autism. You can see the blue dots and red dots are there. In the left panel, you can see that the blue dots which locates where the normal child is looking. So normal child, most of the case, look, the normal child, the concentration of the blue dots is moreover here. That is, the concentration of a typical brain development child, these blue dots represent that this is the position of the eye of the normal child. And red dots represents the location of the eyes where the child with autism looking or watching the video. So each dot, one position of eyes. This is the eye tracking map. Most of the time, in the normal case, looking at the face and not only looking at the face and more concentration of the blue dots on the eye contact of the on the video of the playing child. But in case of autism, that means this case, we can see the red dots are moreover scattered. The child with autism, he is looking around the background, he's looking at the background, the and less time is eye contact. That is important. That is important. That is less time in the eye contact, less eye contact. So gaze is scattered, looking mostly time in the background or body or less time contact. So what is the aim of this study? The aim of this study is that without asking any question to the child who is suffering with autism or something, depression or any type of mental stability. Mental stability is there, if instability is there. So, without asking any question, using simply the social behavior just by watching the video, that is transformed into the objective data. What is the objective data? That is the eye mapping, and we can measure how brain is processing. So, the child is watching the video, right? I am not asking the child that what type of problem you are facing. Child is watching the video, and with the eye tracking mapping, that is from the objective data, we can measure how this is the brain is processing, how much brain is developed, how much problem is there. So these are nice examples of affective computing, we can say. Okay, so foundation of emotions. So how it is formed basically. As we are dealing with the affective computing, we care about stress level, again anxiety level, emotional well-being level. So we need to know the very basics of the emotions, right? That is how emotion forms, from where it is coming, and how we can model the emotion. That is important. So at first, that is what is affect. Affect is nothing but feeling good and bad. Affect is nothing but feeling good or feeling bad, or calm or excited. That means either my feeling is positive or my feeling is negative. That is my raw feeling. Either the feeling is positive or the feeling is negative. Either with the feeling positive, either my energy is high or the intensity is high or the intensity is low. So that is intensity. So that is the simple thing of with the affect. Simple raw feeling. Feeling good, feeling bad, feeling calm, feeling excited, high energy, high intensity, low energy or low intensity. But emotion is a complex and constructed. It is an organized reaction pattern. There are several things are there involved with emotions, right? Say one example. I can say that we have. Say I'm saying I am angry. I am angry because he insulted me. He insulted. So here, what is affect? I am feeling negative. I am feeling negative with high intensity. That is affect. But there is something with the emotion that is appraisal. That means interpretation. How we are interpreting this. That means we are interpreting that he treated me unfairly. So that is from then where the emotion comes. So I am feeling bad. That is not emotion. But I am interpreting that he treated me unfairly, then comes the emotion. So in emotions, at first we have the high intensity, negative, that is the affect, and then the appraisal, then the expression, then the emotion comes, I am angry. Okay, so this is how the what is the difference between the affect and the emotion. So when we are dealing with the emotions, we need to know that it is a complex and organized reaction pattern. Okay, so here you can see that how complex the emotion is. We need the affect, that is VA. VA generally it stands for V for balance and A for arousal. We will discuss later. And some body signals are there. Okay, body states are changes along with the valence arousal when we are feeling good or feeling bad or the high energy or low energy. Then the thing comes, what is the most important thing, that is the appraisal. That is the meaning of the thing, and then the context where I am and where the uh, around me, and then we show the expression. All these things coming together, we get the emotions. So when we are going to recognize the emotions, we need to think all these things, that we need to think the affect, the appraisal, the context, and the expressions. So it is not so easy to feel a person. It is not so easy to feel the emotion of a person. So one example is that when a phone ping, say, that is a simple thing. Spontaneously it is happening. That is the affect. Okay, that is say zero point 0.2, the value is 0.2, 0.8. We will discuss later why it is 0.2, why is there, what is 0.8. Say 0.2 is the okay, the phone is I am a little bit curious about is why my phone is pink. That is we are feeling good. Okay, we are feeling good. But the feeling good is the value is 0.2. Okay, and I'm curious. So that means high energy, 0.8. Okay, what happens right now? And we see now the appraisal comes. Say, as an example, the paper accepted. Okay, that is the appraisal. That is the interpretation. Okay, the paper is accepted. Now where I am? Now office peers are present. The peers are present over there in the office. That is the context. Now expression, smile, or I'm showing the message. My paper has been accepted, and then comes the emotion. That is joy or pride. So without these context appraisal expression, uh, there is simply affect is there. There is no emotion. So this is important that every emotion has affect, but not every affect becomes the full emotion, right? Every emotion has affect, must have the affect, but not every affect becomes a full emotion. That means a cool breeze feels pleasant. I am feeling good. A cool breeze is they are feeling good, but that is a positive effect. But that is not necessarily happiness. Okay, so this is the difference between the affect and uh, emotions. Okay, I'm coming to this point later. What is the process? Okay, so there is a definition. It is proposed in 1981. That is what is emotion. That is affective experiences. Is there cognitive process? Is there physiological adjustment? Is there and behavior? All these things composing all these things together, we get what is known as the emotion. It is a complex set of interactions. Okay, so now very interesting theory. There are two theory. This is the emotion theory. Okay, emotion theory. That is uh, the paradox of philosophical and psychological paradox. That is from where emotion actually arises. Do we run from fear because we are afraid, or are we afraid because we run? The question is tricky. That is, we see the bear and we run from the bear because we are afraid. No, we are afraid because we run. That means emotion causes the action. That means as we are afraid, so we run, or action creates the emotion. That means we run, so we are afraid. According to James Lang theory of emotion, proposed in 1884, it is the most established theory. That is, there is an action which creates the emotion. Basically, that means we afraid because we run, not that we run because we are afraid. This is the very famous theory of James Lang theory of emotion. There is one theory of emotion. Okay, so the thing is that the body reacts first, and the mind after sometimes more mind levels that the reaction is an as an emotion. So at first there is a stimulus, that is a beer, and then there is a physiological response, run or tremble, and then the things come, that is a fear. So we feel fear because our body trembles. Not we tremble because we feel fear. That is according to the James Lang theory proposed in 1984. So what is going on? In brief, if we can say that actually that is simply the reflex arc, the spinal cord. Accidentally, say we touch a very hot object. So what happens? The hand jumps back immediately. Are you showing the emotion? No, we are not showing the emotion. Hand jumps back immediately. What is the path? Actually, it is happening. Signal goes from skin to the spinal cord, that is the central nervous system, and spinal cord bypass the brain immediately. Briefly, it bypasses the brain. No emotion is there. A pure safety motor action. It is a motor action simply. It bypasses the brain. After some time, a bit later, a little bit later, signal reaches to the brain. There are some functioning, there is some mapping zone is there. It process just what happened. Then we think that, okay, that was the dangerous. That is interpretation. That was dangerous. We are touching the hot object. That is dangerous. That is appraisal. Interpretation. Then we feel fear. Okay. So this is the Lang theory. And another theory, that is another theory that is not conflicting the previous one, but is a different theory of emotion. There are six, seven theories are there. These two are the most important theory, established theory. That is the cognitive appraisal theory. Uh, it is developed in 1984. That event does not determine emotion, right? Appraisal does. So how we are interpreting the event? That means emotion is, so we can say that according to this, emotion is event, we have the event, then meaning to it, then meaning to it. Okay, so event does not determine the emotion, the appraisal does. So same event, it can cause different emotions. Okay, so we have an example, say it is raining outside. The farmers thinks the appraisal is that rain will help my crops. Joy relief. Picnic goers say, our trip is ruined, disappointment and anger emotions. And child says, lighting looks magical, curiosity or wonder. Okay, so it is a different theory, but they are not conflicting each other. So one theory, James Lang theory, says that body react first, emotion after, and it is due to the physiological changes. And cognitive appraisal says that theory says that thought and appraisal and interpretation comes first, then emotion after. So this is based on the cognitive interpretation, that is it based on the appraisal, and James Lang theory based on the physiological changes. From these two things, the emotion comes. Okay, so now in this loop, there is a big loop over there. So where we can fit actually the affective computing. Okay, so uh, okay, so at first we can see that there is an environment. Okay, we have the perception. That means we see or we can hear. After seeing or hear, we are in the environment. We see, hear. That means the system inside the body. Okay, and then we have uh, we have context. Say we have context. Uh, Context and body response. Both context appraisal is there, and context and body response immediately. And then the most important thing, the body response is that. What is body response? That means instantaneously several signals coming from the body, from heart, from lungs, from stomach, from skin. It is coming from the body to the brain, right? Instantaneously. And then interception. What is interception? Interception is very important thing. That is brain sensing the body from inside, right? Brain sensing the body from inside. And then there is a brain mapping, and then there is a brain mapping is there. Then there is a brain mapping zone. What it is done, what it is, what is done over here in the brain mapping zone, we have the body signals, right? And brain maps these body signals to affect. Now it comes affect. Then it comes the affect. So from the environment, we see or hear the perception, and then we have the context where we are, and then we have the body response simultaneously, and then body response, the brain feels the body response inside, that is a interception, and then there is a brain mapping zone which maps these body signals to the effect. And now we say we are feeling bad, we are feeling we are feeling positive, or we are feeling negative. That means we are feeling good or we are feeling bad. And then this effect changes the our nervous system, that is autonomous nervous system, and it is a closed loop system. Continuously there is a changing. This is a bidirectional flow from affect. It is a positive feelings, and body states are changing, and body states changing, our feeling is changing. There is a continuous process. Now comes the appraisal. Okay, then comes the appraisal. Okay, then comes the appraisal. Okay, so uh, then comes the appraisal means here we are giving the meaning of the thing. That means we are giving some meaning. Here, here appraisal means we are leveling the emotions. Here we are leveling the emotions. That means we felt emotions, and then we take the actions and regulations, and going back to the environment. And it is a closed loop system. And what is action and regulation? That means nothing but the expression. This is nothing but the expression. Okay. And from this expression, affective computing starts. We see the expressions simply. From this observation, affective computing works. What works? What? That it tries to think about what is affect, whether the person feeling good or the person feeling bad. And also from this expression, affective computing tries to find what is the felt emotion. So this is a typical flow of emotion processing. Okay, and the most important thing is there, that is the appraisal. Appraisal means here where we are leveling the emotion actually. Everything is happening. Interception is there. We have the appraisal now. That is interpretation. It depends on context. It depends on memory. It depends on goals, also learning, all these things. Okay, so then we felt emotion and we express something in our face, in our voice, or in our physiological changes are there, like this. From this expression, the affective computing works, and it tries to uh, detect whether the person is feeling good or the person is feeling bad, and how much is the intensity. Okay, fine. So here the affective computing comes. That is sensors detect the effect. There is a computation of the effects. Then models insert the emotion, right? So we are sensing the effect, right? What we are sensing? That is either face, voice, breathing pattern, signals, or heart rate variability, like this. And then we compute all these signals, and we have the models which infers the emotions, right? So this is the part of the effect sensing, a very simple part. That is, we have the signals and patterns. That is the facial changes, voice, speech changes, and heart rate is changing. So that data we have, the data we have. Then from this data we feed is to the system, and now system learns. As we know, the system learns the pattern. Okay, system learns the pattern, and after that, what is the learning? The learning is that if HR heart rate is increasing and say low, and say face say tense, then we can infer that the emotion is anxious. Okay, so this learning happening inside the system. So this is the effect sensing process. So actually the thing is that signals in, then patterns learn, as we know in typical machine learning problem. Patterns learn, and then emotion emotion estimated. Okay. So Uh, there are different types of modalities, visual modalities, physiological modalities, audio modality, and multi-text modality, and we have the multimodal integration. And visual modality, we have facial expression, body gesture, eye movements. We will discuss briefly the facial expressions over here. And one can use the physiological modality for affect recognition or emotion recognition, audio modality, and the best one is the multimodal integration. If you can fuse all the multiple cues for robust affect recognitions. Okay, so now comes the challenge. This is the challenge. The problem is emotional models. How we can model. This is a very big challenge. Okay, what is the challenge? That is uh, perceived and felt. Okay, so what is perceived? Perceived means what? We see that our friend with tears in eyes is crying. So we perceive sadness, but that does not mean actually we feel sad ourselves, right? Actually, we are not feeling that. We see that person is crying. Yeah, okay. I observe the sadness. This is actually happening in AI system. What is happening? That why it is a big challenge. The person smiles to hide. A person smiles to hide the anxiety. A person smiles to hide the anxiety. Right? Anxiety. AI levels what? Happy. But the true emotion is nervousness. Actually, here actually why it is so? Because AI often identifies the perceived emotion, what it is seeing. The what is the inner feeling? The true felt emotion is totally different, and AI cannot recognize this person. So our challenge, our objective is to overcome this challenge. There are several challenges are there to build a robust AI system which can feel literally a person. That is ambiguity. That is same expression, smile, joy, same expression can mean different things. That is, smile means joy, politeness, discomfort. There are 17 types of smiles are there. There are 17 types of smiles. Okay. And context dependence, AI sees signals, but not the full situation. The personal background is there. Okay. And cultural difference, person to person varies, society to society varies. Data biasness, that is the main problem with affecting computing. That data sets are leveled by the human observers. Okay, fine, but that is a perceived, not for the self report, right? What I am feeling, I'm say I am taking some video of a person, of a depressed person, and I go to the annotators or some some psychological experts that expert sees observes the perceived emotion. Okay, and data sets are labeled according to this. Actually, that is not a self report. Actually, what is the felt emotion that is not reported in the data set? That is another challenge. Okay, so the aim is that what emotion looks like to what emotion truly feels like. So our objective is not should not be that what emotion looks like. That should not be our objective for developing the affective computing model. Our objective should be what emotion truly feels like. That is tough, but can be achieved one day. Okay, so so okay, so emotional model. So there are two types of models. One is discrete and another is the continuous model. Two types of model in emotion model. Okay, one is discrete model, another is continuous model. Discrete models is known as the categorical model, and it is used in largest part of studies because it is easy to use. There are six basic emotions that is proposed by Paul Ekman in 1971, and it is recognized universally. That is happiness. There are six basic emotions are there: happiness, sadness, fear, anger, surprise, and desire. Okay, so what are the advantages? That is, it is easy to implement. Okay, if this is the six basic emotion, it is easily implemented if this is genuine, obviously. If this is the felt emotion, if this is genuine, then the result is correct. If it is pretending, the person is pretending something, the result is not correct because we affecting comedy is not right now. We cannot detect from the facial expression only that what is the inner feeling. Okay. And there is a disadvantage is that it is difficult to model the relationship between the different discrete states. Why discrete state? And also the psychologists prefer also the psychologists prefer what psychologists prefer that we need the continuous model. what is the continuous change in the emotions, not the discrete model. Okay. So hence come the dimensional model is a very interesting and very popular model. Is that it is proposed in 1977 by Russell. This is known as the VAT model or PAD model. So V stands for the balance, A stands for the arousal, D stands for the dominance, or P stands for the present pleasure or displeasure, A stands for the arousal, and D stands for the control or dominance. You can see here that it is a three-dimensional. Uh, this is a three-dimensional diagram, three-dimensional space where we can put the emotions. This is a three-dimensional space where we can put the emotions. Uh, so you can see that this is positive arousal, and this is the part of the negative arousal. This is the part of the positive valence. This is the part of the negative valence, and this is positive dominance. Dominance means the control. That means how much we are in control, how much we are not in the control. That is the negativity. You can see that. Uh, in anxious, one example I can show you, that is the anxious, that is the emotional state, one emotional state. So anxious is minus P plus A minus D. I think this is visible. Minus P means that means the feeling is negative, but the intensity is high, and I don't have any control on myself. So minus P plus A minus D means minus P stands for the feeling is negative. That's why I'm anxious. And plus A, that means the intensity is high, the negative feeling is high, intensity is high, and minus D, that means the dominance is poor. That means my feeling is weak. Okay, so this is a typical range of when the annotators or experts, physiological experts, annotate something, that is valence with -1 to 0, and arousal -1 to +1, and dominance -1 to +1, and different. It is a typical distribution of VAD. In joy, what is the typical distribution? Anger, it is a typical distribution. You can see over here that in three-dimensional space, where is fear and where is anger? It is in the three-dimensional space, and there is joy. Joy means here that means the valence. Valence is the positive here. Valence is positive here, and the arousal is high. Okay, this is the arousal, and you can see that dominance is also high. That because it is joy. Okay, and anger. Similarly, anger, you can see the valence is negative. Everything is positive. Dominance is positive. Uh, I am everything is in my control. That is the anger state, and arousal is high, but the feeling is negative. Okay, so this is the three-dimensional state with which we can categorize or designate the emotional states. Okay, one more interesting thing is that this is known as the circumplex model, eliminating D. Here we eliminate D. Sometimes it is not possible to annotate D. We cannot get the data set with D. It is tough to. It is hard to annotate what is the control in a person. So it is easy to. It can be done with positive feeling or negative feeling or high energy or low energy, but it is sometimes it is not included in the data set. That is what is the dominance or what is the control. So we have it becomes a two-dimensional emotional state. That is, it is positive. That means positive valence. This is negative, negative valence. Feeling good, feeling bad. This is arousal, positive arousal, and that is high energy, and coming. That means here it is the low energy, negative energy. Okay, so you can see that with this 2D model, what is the problem with this 2D model? You can see what is the position of anger and fear, right? So this is the two emotional states. In the two-dimensional space, the difference, the position, the relative distance between the anger points and the fear points are very close. So here lies the problem. That's why we get very poor results on fear. Most of the facial expression analysis we can get if we use for two-dimensional VA, then sometimes there is a overlapping between anger and fear. Okay, these two emotional states. So why? because okay, so mm, D is needed here. What is the advantage of D? The advantage of D is that instead of two-dimensional, if we go for the high three-dimensional, instead of 2D, if we go for 3D, that means if we include D, that is the dominance D, uh, not the dimension, but the dominance D, then what happens? In both the cases, valence negative, arousal high. Anger, valence negative, arousal high. The dominance, in case of fear, dominance is submissive. But in case of anger, the dominance is in control. Say one example that say I want to fight. I want to fight. I want to fight. And uh, another thing is that I can't handle. Okay. I can't handle. I'm in danger. I am in danger. So these two things. This is anger and this is fear. Thing is that I want to fight. That means balance negative. Feeling is not positive, and the arousal is very high, right? But the I want to fight. That means I'm in control. My feeling is strong. D is very high, right? But I can't handle. I'm in danger. So that means I have a negative feelings. Valence is negative. Arousal is high, high intensity. But we have the dominance. That is the control on me. That is, I am feeling weak. So that means I cannot handle. Okay, we are not in control. So there is a two different things that I will attack. Okay, I may be attacked. That is the two different things. In so you can check over here anger and fear as because the difference. Yeah, look at the difference in the dominance. So in both the cases in three-dimensional space, we can see the difference in anger and fear. But in both the cases, B and A are more or less same. You can check here. Anger is negative. Anger, the valence is negative. Fear valence is negative almost. Anger, the arousal is positive. Fear positive. But dominance is 0 + 0.6 and it is -0.6. Okay. So fine. No. Now the another important thing is the signals and pipelines, right? How we can extract the features and how we can get the signal, how we can get the patterns, and what are the flow of the of emotion modeling, right? So feature extraction. This is the handcrafted features we can do. That is the landmark from the landmarks. We can find the geometric features. We can find the eye height, eye regions, expected nose region, or something like this. And all these things, all these are the vertical projections. We can put the vertical projections of the uh, nose region or area of the mouth or the distance between the landmarks like this. So this is the handcrafted features. Uh, one handcrafted features is this geometric feature. So what is the disadvantage of handcrafted features? That is several disadvantages are there. Okay, that is we actually from geometric features we are getting the wireframe. Like that means the points are there. That means these are the geometrical points. That is we are getting some wireframes, right? Not the scheme or textures, right? Like wrinkles or if there is a fold. The texture information is not there in geometric features. And also, geometric features alone is insufficient for some action units. I will discuss what is the action units. That is AU6, AU7. These are the two action units in a phase. In both the cases, we can see that for the geometric features, we will get the same result. Okay, so that is another limitation. Later, I will discuss what is action units and how it comes. Action units is very important for emotion recognition. And also, the problem with the geometric features is that very sensitive to pose, uh, very sensitive to occlusion and noisy data. In real-time data and real data in the wild, we have the pose, occlusion, and noisy data. So in that case, it is better not to use the geometric features. Okay, so different experiment. So it's very interesting experiment that is known as a diffusion experiment. What the modern day facial expression science or facial expression recognition started from here. Okay, what he has done. So Dushan used electrical spikes, electrical shocks. So this is the electrical shocks. Okay, at different face muscles of volunteers. Obviously, he is a volunteer. He used some electrical shocks on different face muscles. And what was the observation? Observation was that if I activate this muscle, what visible change do I get? Right? What visible change do I get? If I activate these type of muscles, if I activate eye muscles and mouth muscles, what type of changes I can observe in face? So this was a very interesting Dushan smile, sorry, Dushan experiment, and from where the genuine smile is known as the Dushan smile. Genuine smile. All the smiles are not genuine. Only the Dushan smile is genuine. So it involves the eye muscle AU6 and AU12. Why AU6 and AU12? I'm coming later. So what he observed that if there is a genuine smile, then the eye muscle and the mouth muscle is activated. In other way around, we can say if we activate the eye muscle through electric shock, okay. If we activate eye muscle or mouth muscle, the person shows the genuine smile, right? Or in other way, we can say different way. We can say if there is a genuine smile, then obviously there is a mapping in a muscle. There is eye muscle and mouth muscle. There is a change. So if we can detect the muscle movement, which muscles are associated, we can do or we can infer the facial expression, and that is the emotion. Okay. So later, these later the AU, that is known as the facial action coding system FACS, it is introduced by Paul Ekman. Different uh, he break he broke all the faces into a small blocks or small units. It is called the action units. So there are several action units are there. So one is say one to actually in 1978 there are actually 46 such action units. So each action units encodes the facial muscle activations. Okay, just like AU45, there is a blink. AU6, cheek razor. AU5, upper lid razor. So when we are getting the data set, or we are building the data set, when we annote, we specify the active action units which corresponds to the muscle movement. So from this muscle movement, from these action units, or from these facts, we can detect what is the emotion, what type of emotion may be there. Okay, so you can see there is a genuine smile that is both AU6 and AU12 is high. Okay, AU basically AU is annotated 0 to 5. AU is annotated 0 to 5. 0 means absent. No AU is there. Different AU, multiple AU may be there in facial action. If you have in faces, multiple AU is there. Okay, so in case of DISPA data, in case of this data set. So AU 1, 2, 4, and almost 14 uh, types of action units are given there. So 25, 26, 25, 26, all these action units are given there. Okay, so happiness person, this is the Duchenne genuine spine or Duchenne spine, genuine spine, because there is a cheek razor and lip puller. That means AU12 and AU6 is there. What is AU6? That is cheek razor, and what is AU12? That is lip corner puller. So detecting these action units, we can say that okay, this is the uh, I mean to say this is the actual genuine. Okay, okay. So one simple modeling from use to emotion, that is, say we have the action units, presence, intensity is given from 0 to 5. So we have the database, say we have the data, DISPA data set. So what we do, that is, uh, from annotators, we can get the values of 0 to 5. and then we are using facts. Okay. Then stage one, we can input the faces in the transformer, which predicts the use from pixels. A very simple block diagram. It is stage one that we input the faces, we feed the faces in CNN or transformer, which predicts the use from pixels, and then CNN or transformer predict the use. We are getting the AU vectors. Then then we have a small MLP model, multi-layer perceptron model, which maps the AU to the classification model, either to the classification model, this is the discrete emotion, or we can go for the valence arousal. MLP can be used here, the MLP multilayer perceptron can be used for discrete emotion, or it can be used for the regression purpose, or you can use the linear regression for valence arousal estimations. Okay, so this is, remember one thing, that is the multi-level AU. This is multi-level. Uh, Multi-level AU present is there. In case of multi-level AU, uh, we need to change the output layer. So output layer is changing. If AU say 1, this is for AU2. Whether AU present or not, 0 or 1. Whether AU2 present or not, 0 or 1. Whether AU say 26 present or not, 0 or 1, like this. Okay. So in the last layer, we need to be careful when we are dealing with the multi-level. Okay, right. So there are different types of features. I'm not going in details. We can extract from use the different types of features for fear, anger, and disgust, and happiness. Happiness, recently it is showing that intensity of smiling predicts the longevity. It is the research is proposed in 2010, 15 years later, 15 years ago. So no smiles 79, 72.9 years, and Duchenne smile 79.9 years. Interesting findings. Okay, there are 17 types of smiles. If anyone is interested, what are the 17 types of smiles are there? I would like to suggest to go to the poll of Ekman group in the web page. What are the different types of smiles are there, and what is the different smiles? How we can classify those? Okay. So now the joint learning, the categorical emotion, and continuous balance arousal. So how we can do that? So we have extracted the features. We have the emotion models. We have the categorical models. We have the continuous models. Everything is that. Now the pipeline. What is the pipeline? How we can deploy it? Okay, in our machine learning model. That is the actual effective computing. Okay. So here it is uh, published in Nature Machine Intelligence. One of the author is Pantic, Maja Pantic. If anyone interested, and go through Maja Pantic, several notable works are there. Okay, so what is the traditional approach? Traditional approach is that I think so. There is an input image. The first stage is face detection, simply cropped faces, and from the cropped faces, we are estimating the facial landmarks. Some convolution neural network is there, and from the facial landmarks, we face align. We There is a face alignment. Then the aligned image. Okay, and then the aligned image, we are going for the joint learning. That means the categorical emotions and the continuous levels of balance arousal. So there are two different heads are there. One head is for discrete emotions, and one head is for continuous emotions. That means balance arousal, and this for the class. That means whether it is happy or not, or joy, everything is there. But what is the problem with this type of traditional thing is that it is a long pipeline. We need two, three architectures. Okay, there are two separate heads over there, two models over there, no sharing of information. Okay, what it is learning, what this model is learning, actually this model is not being shared with this learning. Okay, so sharing is important, right? What Pentics suggests, that is a totally different thing. That is input image. We have the face detection, cropped faces is there, and then the total facial landmarks categorical, and continuous effect estimation, a complete loop is there. A single block. There's a single backbone. Okay. All the three heads are there. No separate heads are there. No separate heads for VA, no separate heads for categorical emotions. But all the heads are over here. Only what we are getting at the output, like we are getting the facial landmarks, we are getting the categorical emotions and continuous level of balance and arousal. So over here, this is the process of multitasking. We can say this is the process of multitasking. Okay. This is the process of multitasking. So different task is there. A single backbone is there, and this backbone is used that is ResNet 50. Say. So this is multitasking. There is a facial landmarks are there. We are getting the categorical emotions and balance arousals. And what is the advantage of this? Uh, there is a shared features, and also what is happening as we are predicting as the optimizer over here, as the optimizer is trying to align the landmarks forces the geometric attentions. That is, landmarks is the geometric attentions. And again, VA captures the intensity. And all this information, the category layers are getting. So this is the flavor of the shared learning. That means what category is learning, what VA is learning, what landmarks is learning, all are shared, right? And as because all are shared, it is most generalized. As because it is generalized, working is less. As so that means we are getting a more generalized generalized architecture. And simultaneously as because it is optimized. So it is a very important uh, architecture. It is known as the immonate. Okay, so it is known as the immonate. Right. Okay, so what are the over here for joint learning? That is evaluation metrics for emotion recognitions, different types of RMSE. Important thing is that not only a single loss is there. So here at the output layer, we have the
Respected
categorical.
sir,
Yes, yes, yes.
sir, requesting you to summarize the key points so that we can move towards the interaction session as well as the question answering. Okay?
Yeah, yeah, yeah. Okay, so give me 5 minutes. Okay,
Yeah, yeah, yeah. You can, you
yeah,
can.
yeah. Thank you. Okay, so in this case, we have the composite loss. But you can say that we combined all the losses, category losses, MSC and LCC, all these things. Okay, and also we can use the knowledge distillation loss. Okay, what is knowledge distillation? I don't have some time. I can explain that what is knowledge. Anyway, so this is one of the architecture we can use in emotion recognition. I can show you that. Is it visible, madam? Is it visible?
Yes, sir, it is visible.
Okay,
Yes.
okay, okay. I'm explaining this part. That is, this is the response of the Emonet. What we are getting the balance arousal estimation. You can see each and every screen that corresponding to the faces where it is angry or where it is fear, the red dot is coming. So here it is a present. That means the positive feelings we have, and we have okay, this is neutral but high feeling, and here again it is a positive feelings. And look over here, that is a fear. Okay, sad, and here it is angry. The position is continuously changing. Okay, so this is the valence arousal estimation. From this continuous framing, we can say that that is the results they have got in. So uh, so I would like to show some examples in applications. Emotional robot. The applications is that was proposed developed in 1997 1997. Creator was Cynthia Basil from MIT lab. Recognize it can recognize the tone and facial expressions. Okay. Okay. Can you hear? Look, this is the model. That is the emotional model. This is happiness. Okay. This is the happiness, interest, sadness, surprise. The emotional word. Surprise, tired. So this was developed at MIT lab, and that is emotional robot which can recognize the tone and the gestures and all these things. 1997. Okay, and now in 2024, what we have, that is the emotional model where we have, that is this one, Amica and Nazi, engineered arts developed in UK. Okay, so this is the emotional robots. So there are some facial expressions if they are okay. So this is where we are now, and there are empathetic robots. So the empathic robot, that is Paro, Robin the robot. This is helping the pediatric and elder care company and reduces fear and loneliness and get kids with games. This is the application for all the world, and we have um, Nodulas face reader emotions there. So there are several tech applications. Voice biomarkers are there. Okay, so thank you for this session.
Thank you, sir.
Thank you.
Now we are proceeding towards the interaction session as well as question answering. I'd like to request all the participants to write down their question on the chat box so that I can forward it to the speaker and he can answer it also. One by one, please write down or raise your hand so that we can understand you have a question and I can forward it to our honorable speaker. Once again, I'm requesting the participants to just write down their questions for the speaker. Okay, please write down the question. The question is, sir, the question is, using AI tool of effective computing, can we predict human or any animal's emotion? The name is showing unknown user. I don't know who he is, but the first question is, using AI tool of effective computing, can we predict human or any animal's emotion? PB sir, am I audible?
Okay, can you hear me?
Yeah. Yes. Sir, may I
Okay,
repeat the
so
question once again?
no, the question is already that is AI using AI tool of effective computing.
Yeah.
Can
It's
we predict
visible.
human?
Yeah,
Can we
yeah,
predict human or animals' emotions? So,
yeah.
um, if we can extract the features, the answer is if we can extract the features from facial expressions or from uh, physiological signals, maybe to some extent we can do that for animals, but human we can do. Okay, no issues.
Okay. Okay. Next question is from Abhishek Banerjee. Can temporal models like LSTM capture emotional transitions better than CNNS for processing emotional transitions?
Can LSTM capture models like LSTM? Yeah, but in case of video frames, basically, in case of video frames, we generally use the bidirectional LSTMs. So, but in general, LSTM is not better than CNN. Okay, they are basically the applications are different. Okay, application types are different. For images, CNN pattern detector in space, and for audio signals, 1D CNN we can use. But in case of LSTM, the sequences or sequence order, that is, if we use the video sequences, or in case of the memory is there, then we can use. Okay. So if there is a long-term dependency, then we can use the LSTM.
Okay, sir. One second, Abhishek Banerjee is typing something, so I'm waiting for that. How to reduce model bias when emotional expression varies across age groups for different persons?
Sorry, how?
Next question. Is it visible to you, or else I have to repeat it, sir?
Yeah, okay. How to
Yeah.
reduce the model bias when emotional expression varies across age groups for different persons, we have different types of expression models we can build. And actually, what type of model bias, how we can, what you are expecting from, I'm not understanding that model bias means underfitting problems or something like this. Please explain. So can you, what are you telling that in case of that, say we are training our model with say in the age group of 20 to 40, and in case of 40 to 60 and different models. So when we are evaluating the model with age group 20 to 40, and we are evaluating the training the model with age group 20 to 40 and evaluate the model with the 40 to 60, then there is a problem. Okay, because there are some facial muscular changes will there. Person to person, yes, person to person it varies, belong to different age groups, right? So in that case, we need to share the information. Shared information is needed. Obviously, for class A data, if it is trained with the class A level data and we go for the class B levels data, so there is some problems. The model is not trained with the age group for 40 to 60. The model is trained for, it is highly biased for 20 to 40, but it is not actually helping for 40 to 60. One thing we can do, that is we can use the rich backbone for some, it is say for self-supervised learning. Okay, when the levels are not there, or we can go for zero shot learning when the levels are there, but we don't have the class. Okay, so generalization, yes, how build a generalized model? Yeah, the question is clear. That is how we build a generalized model. That means uh, actually in that case, uh, we need to use what we need to use a right backbone. Okay, so ResNet 50 or VIT 16, something like this. Vision transformer or something like ResNet 50 trained on huge phase databases, okay, 300 million databases, and then it is fine tuned. There is a model, Moda Creator. Moda Creator. You can get it from Hugging Face. Okay, Moda Creator. So from Moda Creator, this it has the generalization capability because it is trained on FIEM 013. It is trained on MMI database. It is trained on AffectNet database. So AffectNet database has 4 lakh images. MMI database has 4 lakh images. If we go for the transfer learning or some self-supervised learning, through this, we can use this is as a backbone. So there are several types of features are there. Uh, okay, so we can do it. We can generalize our model. We cannot generalize our model by training from the scratch. We can use the, it is better to use the, what should I say? It's better to use the backbone. Okay.
Okay, sir. We are running out of the time. Okay. Thank you, sir.
Yeah.
Thank you
Okay.
for all of your responses. And
Okay.
it's my privilege to propose the vote of thanks on behalf of the organizing committee of this faculty development program. First and foremost, I extend our heartfelt gratitude to our esteemed speaker for delivering such an insightful, enriching session. Your expertise, clarity of thought, and practical perspective have truly enhanced our understanding. We are deeply thankful for your time and effort. My gratitude goes to our respected executive director, principal sir, the conveners and the coordinators, and all the participants for their active involvement. Now I'm going to hand over the session to our respected coordinator, ma'am, Dr. Rupa Bhattacharya, for further activities. Thank you, everyone.
Okay. May I leave?
May I
Madam,
leave
may I
this?
leave?
Yes, sir, you
Yes.
may leave.
Oh, okay.
Yeah.
Thank you. Thank you.